Okay, so even if you take calculus at the high school level or the college level, you're going to see a problem like this, almost guaranteed. Ladder is up against a house and it starts to fall. It starts to go towards the ground. We have a 13-foot ladder and it starts to slide down, and by the time it's a certain distance away or a certain distance down, it's moving a certain speed, a certain rate of change. In our case, we want to figure out what we have when we have a 5 foot away from the house and it's moving away from the house at 12 feet per second on the base here. We need to figure out what is the rate of change of the height of the top of the ladder, what is the rate of change of the area of the triangle for some reason, and what is the rate the angle is changing between uh, the base of the ground and the ladder. So let's look at the first part of this question. What is the rate of change of the height of the top of the ladder? So if this is, we'll call this side of the triangle Y, we'll call this side of the triangle X, and call the ladder Z. So we know that x squared plus y squared equals z squared because this is a right triangle. This is a house that's sitting pretty level on ground. If we take a derivative of this, which we saw yesterday, we got 2x dx dt plus 2y dy dt plus, or equals 2z dz dt. Notice I did all that without plugging any numbers in. We plug in the numbers at the end. So here we say it's 2, we want it to be 5 feet away from the house. At that instant, it's moving 12 feet per second away, plus 2, if this is 5, this is 13, we could do Pythagorean's theorem to figure out what y has to be at that instant. So, let's see, 5 squared plus y squared equals z squared, or 13 squared in our case. So 169 equals 25 plus y squared. If I subtract y, or 25, I get 144. So the distance there is a nice even number 12 at that specific time. So I'm going to plug 12 in for y. dy dt, how fast is it moving down? That's what we're trying to figure out. Equals 2 times, the ladder's not changing, so it's 13, but it's not changing, so there is no dz dt. It's not collapsing, so this whole thing over here is 0. So let's see, 5 times 2 is 10, 10 times 12 is 120, plus 2 times 12 is 24, dy dt equals 0. So 24 dy dt equals negative 120, and if I divide that out, dy dt is a negative 5. We're in feet per second. So that's part A of the question. Part B of the question, what is the area of this triangle, or how's the area changing as it's sliding down? So area of a triangle is 1/2 the base. The base for us is x times the height, which we called y. So since both of those are changing, we have to do a product rule. Nothing's staying constant. So we saw that a couple days ago. So dA dt is 1/2 times derivative of x times y, which we know is a product rule. So we have x dy dt plus y dx dt. First times derivative of second plus second times derivative of first. So now let's plug in what we know. We want to figure out what dA dt is, so it's already by itself. That's good. Equals half x. We wanted to be at 5. dy dt we just figured out was -5. Plus y we said was 12. And dx dt we said was also 12. So we'll multiply this out. We get that dA dt is, let's see, 1/2 of -25 plus 144. So, let's see, 144 minus 25 is 119, half of 119. I'm just going to leave it like this, 119 over 2. And units would be area, which is feet squared per time, we said is seconds. And then the third part of the problem, I'm going to erase this part here. I'll do it right there. Let's see, part C. At what rate is the angle between the ladder and the ground changing? Well, the angle, if we're talking about angle, we're usually talking about trig. So I'm going to express this in trig. And you could choose anything, really. I'm going to choose sine of the angle. Its opposite, which is y, over hypotenuse, which is z. Or I'm going to just put 13 here since it's a constant number. It's not going to change. And do a derivative. So derivative of sine theta is cosine theta times derivative of the inside, which is d theta dt. The angle's changing, so that makes sense. Equals the derivative of y, which, let's do it this way, 1/13 times the derivative of y, which is dy dt. We figured out that the dy dt was -5, so we could plug that in. That makes this side -5/13. We want the rate of change, d theta dt. And if we divide both sides by cosine theta, this side over here actually would become secant theta. Remembering that 1 over cosine is secant theta. So, without knowing what the actual angle is that they want, this would have to be my answer. Oh, we do know the angle that they want because we know what y is and we know what x is. So we could pull out regular trig. Let's see. If we want to figure out the sine of theta when we have y is 12 and z is 13, if we do an inverse sine of 12/13, we know what theta is. Which we get 67.380 degrees. We plug that into our formula and we find out that at that specific time d theta dt equals -5/13 times secant of 67.380 approximately. And if you did it, and you did it correctly, you should get -1. I believe we're in degrees right now, so this should be degrees, not radians, per second. Which it's decreasing, it's going down to 0, and that makes sense.